Okay, so let's continue to talk about P and NP completeness. Okay, so let's start with reductions again. So what do we mean when we say a problem A reduces to problem B? Okay, so let's dive a little bit deeper into that. Like, we've been talking about this this is the third class now. But in general, what we mean when we say A reduces to B is we can transform every input to problem A into an input to problem B, such that the answer remains the same. Okay, so that's just that's what the English word reduction means. Like A is a special case of B. Okay, pictorially, if I draw the diagram, right, I have problem A, so these are all the instances to problem A, right? Problem A, some of them are yes and some of them are no, right? We're only concerned with decision problems, and these are all the these are some of the instances to problem B. And essentially, when we say A reduces to B, is we can transform. There is a way to map instances from A to B, such that the yeses go to yeses and the no go to no. Okay, so that means that if we had a solver for B, we can use it and convert it to a solver for A, right? Like we can transform any instance of A into another instance of B. Okay. Yeah, and that's why it's important, right? That's why in all these reductions that we do, we check that the yeses go to yeses on this side, but we also check that the yes here correspond to a yes here, right? Which is the same thing as saying the no go to no. Okay. That's important, right? Because that's ultimately, we want to say that if we had a way to solve problem B, then we could also use it to solve problem A. So A is a special case of B, right? So B must be a harder problem, right? So we want the yeses to go to yeses and the no to go to no. Otherwise, right, the information that we get from the B. Oh yeah, the USB-C port. Oh yeah, thank you. This is the only meaningful way to transform things, right? I mean, otherwise, right, you could map every instance to a yes instance of B, and that's not really interesting, right? Because that's not, it's not giving us a way to compare the problems in any meaningful way. Okay. All right. Yeah. Okay. So does this make sense? Like, what do we want when we say a reduction? Like, we just want a way to transform problem A to problem B. Okay. So that the answers are meaningful. Okay. So that if I had a way to solve problem B, like I said, it will help me solve problem A. Okay. Right. So that's why the direction in which we do the reduction is important. When I say reduce A to B, right? It's really the case that it could be the case that not every instance of B, right, is mapped to some instance of A. That's okay. We don't care about that. All we care about is every time I have some, I need to solve a problem in A. I want to solve problem A. I get an input. I can just somehow transform it to a problem in B, such that the answers help me solve the original A problem I care about. Okay. So yeah, and we've done a bunch of reductions so far, and you can check that this property holds. The answers I get in the mapped instance, right? When I turn a for example, the first reduction we did, right? We turned every 3-sat instance to an independent set instance, such that the answer there was actually the right answer here. Okay. Any questions about reductions? It is confusing, right? Because you have to get the direction correct. But yeah. Any questions about anything that we've seen so far? Okay, so now let's just see a bunch of examples again, okay? So now I'm going to introduce more problems, and we're going to see connections between more and more problems. Okay, so the first problem is called subset sum. So one way to write this problem is the following: I give you a set of numbers, okay, and a target value. Is there some subset of the numbers that adds to that target value? Okay, so it's called subset sum. Okay. It's a yes or no problem, right? It's a decision problem. Okay. Now I'll tell you another problem. It just seems related. It's called the partition problem, which is I give you, again, a list of the numbers. Can I divide them in two groups such that each group has the same sum? Okay, that's why it's called partition. Like, can I divide it into, partition it into two groups that, such that the sum is the same for both groups? Okay. So these are just two problems, right? Two computational problems, right? So now we're going to see reductions between them. Okay. So yeah, I mean, this is the subset sum, right? I give you a bunch of numbers, and I target sum like 15, and then these three things add to 15. So that's a yes. And then partition, it's just I give you a list of numbers. Can I divide it into two groups that have the same sum? Okay. Any questions about subset sum, partition, what the definitions are? So there's just two computational problems. Okay. And now we're going to show, right, like previously we've done, essentially the reason we do reductions is to prove NP completeness. But let's take a step back and just say, OK, I just want to show you a reduction from partition to subset sum. Okay. So again, what that means is, right, every instance to partition, every input that I give to partition is actually secretly an input to subset sum. Okay. So I want a way to map an input to partition to that of subset sum, so that, right, so what that means is, like, right, if I have a way to solve subset sum, then I can solve partition. Okay. All right. So so what is an input to partition? Right, it's just a set of numbers, and I ask, can I divide it into two groups of equal sum? Right. So I want to turn this into a subset sum problem. Right. The subset sum problems needs a target value. So naturally, right, what is the choice that we use? Which is just like the sum that comes from the partition problem, which is half of the total sum. Okay. All right. So to transform a partition input to a subset sum input, we just take our input and we need a target number, right, for the subset sum problem, and we just set the target number to be half of the total sum. Okay. So now we need to check that a yes instance go to a yes, right? Like it's a yes if and only if the other thing's a yes, right? Right. Like this reduction is doing something interesting, right? So that's what we need to check. Of course, like, all the reductions take polynomial time in this class. So here is one example. Okay, so right, I give you an input to partition. Okay, I want to solve partition, but what is reduction? I want to solve one problem using an algorithm for the other problem, right? So I just need to transform the input. I don't care what the other algorithm does. That's not the point. The point is to show that a problem is a special case of another problem, right? It's to establish hierarchy between problems, okay? So I just need to transform inputs, right? So I have an input to the partition problem, right? This list of numbers, right? What I do, right? I need an input to a subset sum, which is I just need a target value, which I do half of the total sum. And then, hopefully, right, a yes or a no answer actually corresponds to the right yes or no answer here, okay? Right? Then that's a meaningful reduction, okay? Okay. All right. So before we argue about that, like, at least as the high-level strategy makes sense. Like, why did we choose that target sum? Well, right, if I had a subset with that target sum, the rest of them also have to have the target sum, right? Because it's half of the sum. So that would give me a partition, right? So that's why. Okay. All right. So let's just prove, right? So let's just say, right, so we need to prove two things, right? A yes goes to a yes. All right, so first, right, let's assume that the input to the partition problem was a yes instance. Then I want to show that the input that I feed to the subset sum part is also a yes instance, right? Well, if it's a yes instance to partition, right, that means there was a way to partition in half, and one of them is a valid subset for the subset sum problem, right? So a yes goes to a yes. Okay, one way. And then now to check back, right, like, what does it mean that the input was a yes for the subset sum? There is a subset with half the sum, but then the other half has the rest of the half of the sum, right? So that would give me a partition, okay? So again, let me just go back, right? Like, what happened, right? A yes went to a yes, and similarly a yes went to a yes here, right? Another way to say it is like a no goes to a no, okay? Right. So it's right. So when we do the reduction, right, a yes goes to a yes, and a yes here also goes to a yes. Okay, that's what we need to check. All right. Okay. Any questions about how this? Let me just go back to the diagram. Any questions about how the reduction went? Right. Right. So again, what this shows is like partition is a special case of a subset sum, right? If I knew how to solve subset sum, I could solve partition. What I would do is, right, I would take the partition input, just get a target sum, which is half the thing, half the sum of the values, and plug that into my subset sum solver, right? It would say yes or no, and that would be the right answer for the partition instance. Okay. Any questions? Right. So the whole point of reduction is to just recognize that like problems are just like special cases of other problems. Okay. That's the point. Okay. All right. Does the proof make sense? Like, right? If it was a yes instance to partition, right, we checked that it was a yes instance to subset sum. Similarly, we checked that if it was a yes to subset sum, it must have been a yes to partition, right? That's another way of saying that a no goes to a no. Okay. Okay. Right. 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 It's like called the counterpositive, but just think about it like logically, right? Like I said, anything that mapped to a yes here must have started with a yes. So it cannot be that a no goes to a yes. So a no must go to a no. Okay. That's what we checked. Okay. But if that confuses you, just think like, right? We just made sure that like the transformation we did was like interesting, like actually meaningful, right? The answer that I would get would correspond to the right answer that I care about. Okay. That's essentially what we have to check, right? That's what reduction means, right? It's like a special case of another problem. Okay. Okay. Any questions? Confusion? What the subset sum problem is? Partition problem is? And like how we related these two problems? Okay. All right. So what this reduction did was, right, it turned every partition instance to a subset sum instance. Okay. Right. Like I said, so a yes for partition, if and only if it's a yes for subset sum. Right. Ultimately, what this means is if I had a way to solve subset sum, then I can solve partition in polynomial time. Okay. I do this transformation. I plug it in. Whatever yes or no I get is the right answer. Okay. So I'm just saying like the same thing many times, just because, right, it is a tricky thing, right, when you first learn about reductions, like which way the logic goes. Okay. All right. Okay. So let's just move on. Right. So right, this reduction would imply subset sum is NP complete if we knew partition was already NP complete, right? But we don't know that. I haven't told you that yet. Okay. Okay. But let me tell you something. I'll say, okay, you can take for granted that subset sum is NP complete. So it turns out it is. It's a little bit hairy to prove, but I'll give that to you for free, right? I'll tell you subset sum is NP complete. Does the reduction we did, like, does that say anything about the partition problem? Does it say anything about the NP completeness of the partition problem? Why or why not? Yeah. Yeah, exactly. Yeah, that's exactly the reasoning we're looking for, right? All I showed you was that subset sum is a harder problem than partition. If I tell you subset sum is a hard problem, it doesn't say anything about partition, right? Like, sorting is reducible to 3-sat, okay? Because sorting is in P, right? If I ask, okay, is this array sorted or not? That's a problem in P, right? I can check in polynomial. Like I can solve the problem in polynomial time. So it's in NP, right? 3-sat is NP complete. So sorting is reducible to 3-sat in some convoluted way, okay? 3-sat is NP complete, but sorting is in P, right? So like, it goes one way but not the other, right? If I say subset sum is a hard problem, it doesn't say anything about easier problems, okay? So which way would I need to prove like if I just tell you subset sum is NP complete, and I want to say something about the partition, which way should the reduction go? Yeah, I should go the other way, right? Like, I actually want to show that subset sum is a special case of partition. Okay, so that's what we're going to do next. We're going to show that subset sum is actually also reducible to partition. Okay. Okay. And then I'm going to tell you for free that subset sum is NP-complete. You can just believe that. And this would imply partition is also NP-complete. Okay. Yeah. So the thing about actually subset sum, let's just take a detour, is like there is a way to solve subset sum using dynamic programming. So you can actually kind of think like how you do that. But then the running time is not polynomial. It depends on the total sum. Like that will appear in the running time, so that's not polynomial. Okay. But that's like an exercise that you can do on your own. Okay. But for now, we're going to show that subset sum, right, can be reduced to partition. Okay. So it turns out actually that subset sum is also a special case of partition. Okay. So that's the funny thing about these reductions. That problems are like reducible to each other all the time. Okay. You just have to be like, you just have to imagine them in different ways. So it's not like a strict ordering of problems, right? All NP-complete problems are reducible to each other, okay? They're all special cases of each other. So if you solve any one of them, right, you solve everything in NP-complete. Well, you also solve everything in NP, right? That's what it means to be an NP-complete. Every problem is reducible to you, okay? All right, so again, these are the definitions of the problem, right? Subset sum is I give you a list of numbers and a target value. I tell you the target value. Does there exist a subset of the numbers that adds to that target value? Partition, right? I give you a number. I give you a list of numbers. Can I divide it in half so that the sum is the same? Okay. And I want to show you that, right? Previously, we showed partition can be reduced to subset sum, but now I do the other way. I want to show you that subset sum is actually a special case of partition itself. Okay. The interesting thing is, right, subset sum has this parameter t, right? I give you the target value, but partition doesn't. So we need to be slightly more clever about how we design the reduction, okay? So at least as the goal makes sense, we want to show subset sum is reducible to partition, okay? Any questions? All right, like, okay, so what does that mean, right? I give you an input to a subset sum, and I want to show you I can transform it to an input to the partition problem, right? Because, right, what is a reduction? That means if I had a way to solve partition, I could solve subset sum. So subset sum is an easier problem than partition, okay? So that's where we're going. So I give you an input to subset sum, right? What is the input? A list of numbers and a target value, right? And I need a way to come up with the partition input, okay? The partition input has no target value, right? Just I give you a list of numbers. So somehow I need to like encode the target value in the subset sum problem somehow in the partition problem, okay? So the first step is I'm going to add up all the numbers in the subset sum instance, okay? I call it big W, okay? The sum of everything. All right. And now I'm going to create an instance of the partition problem as follows, right? I have my original numbers that I get for the subset sum problem, but right, I can't put a target value, right? That's not the input to the partition problem doesn't doesn't say anything about a target value. It doesn't accept a target value. So to kind of to get around that, right? What I do is, right, I have this target value t. I add a new number, t plus 1. And then I add another new number, w minus t plus 1, where this w is the sum of everything here, okay? Right, so I took my instance to the subset sum problem, and I created an instance to the partition problem, right, in some way. And now I want to check that if it was a yes to the subset sum problem, like there is a subset that hits this target value t, then there's a way to divide the things in half with equal sum, okay? That's what we want to check, right? We want to say a yes goes to yes, and then, right, like, if it was it's a no here, it should go to a no here. Another way to say that is a yes here would also go to a yes here, okay? But if that confuses you, just think like, right, we have to check that this reduction did something interesting, right? The solution I find here actually corresponds to the right answer there, okay? Okay, so that's what we need to check, right? The original input to the subset sum is a yes if and only if the transform thing becomes a yes, okay? Right, so that's what we're going to check. Okay. So we're going to have to do a sum calculation first, right? The first calculation we do is, okay, why am I doing this calculation, right? Just think at a high level, right? The partition problem cares about dividing things in half. So I should know what the total sum is, okay? And I already know, right? I already know that the sum of all these numbers is this big W. I add another W, that's 2W. The t's cancel, and I get a plus 2, okay? So all this is saying is, first let's check that in the transform instance, the total sum is 2W plus 2, where W is the sum of the original numbers that I get for the subset sum problem, okay? Okay. All right. And then, right, like for it to be a yes to partition, each of the two halves must have some W plus 1, right? So that's just something that we note, okay? And now we're going to use this information to show that, like, a yes, if I could divide things in half, then that one of the halves would correspond to the subset that I'm looking for in the subset sum problem, okay? Yeah. Yeah, so we'll see that in a bit. Yeah, that's like the main trick. So we'll see why that trick was done. Yeah. Okay. All right. Okay, so now we need to show a yes goes to a yes, okay? So first, let's assume that the input I got was a yes for subset sum, right? Then I need to check that the input to partition I get is a yes. So what does that mean, right? There is a subset that adds to t. And then if I just include that, the subset that adds to this target value, plus this extra number, right? The t cancels, and I get W plus 1, right? Which is half the total sum, okay? All right, so it's kind of like, it is very clever how this was done. It was done so that things magically cancel, okay? So first, let's check the easy direction. If it was a yes to subset sum, the thing I get at the end is a yes to partition, okay? Right? Basically, I take the subset that adds to the target value, and if I like augment it with one more number, right? This number, right? The t cancels, I get W plus 1, which is half the total sum, okay? But I need to check the other, right? This is exactly half, so it's a yes or partition, okay? But I need to check the other harder case, which is if the transform thing happens to be a yes, then I can actually find a subset, okay? So now let's assume that the transform input is a yes to partition, right? That means I can split these new, the old numbers plus these two numbers in half somehow, and I get half the total sum, W plus 1. Right? But now I have these two new elements, okay? And the claim is that these two new elements cannot be together in one group if it's a yes to partition. Why? Right, so yeah, let's take a step back, right? So I'm saying, right, I get a new input to partition, and I say, okay, assume, like, let's say y was a yes to partition. It cannot be the case that both of these numbers appear together in the partition. Yeah. Yeah, exactly. Like if they, that's almost it. If they appeared together, then the sum would already be too much. Okay, it would already be too much. So they must be in different sets. Okay, so okay. And then right, they must be in different sets. All right. And then I check which. Okay, let me just go back. Okay? This is just like elementary math, but then I check which set this thing is in. Right, this number that I knew added. I know whatever set this new number is in, the rest of them have to add to W plus 1. That's half the sum. But right, this is W plus 1 minus t. So then if I take it out, I get t. Okay. All right. That's why this was like designed this way, right? I know that if this y thing is a yes to partition, I can split these numbers in half, and each half would have some W plus 1. I look at the half that this last number is in, right? Must be in one of the halves. Together they add to W plus 1. So if I take this number away, they must add to t. Okay? That's all I'm saying. So that's all like this thing is saying, right? It's like if it's a yes to partition, it must have been a yes to subset sum, because I'll show you a subset that explicitly adds to t, which is whatever partition that this last number ended up in, I take that away, right? It cannot be together with the other fake number, so the other things must add to t, okay? That's all this is saying. Yeah, I mean, this is, this is a lot of, I mean, not too many calculations, but just like it's intuitively, once I break it down to you, right, this w minus t plus 1 plus whatever adds to w plus 1. So the whatever part, right, adds to t, which is exactly the subset I'm trying to find, okay? In other words, right, right, we check that, right? If it was a yes to the subset subproblem, it becomes a yes. And then we need to check the other direction, right? If it's a yes here, it was also a yes there, right? Okay, that means the reduction is valid, right? Like whatever answer I'm getting down here is actually the right answer that I get for the original problem, okay? And the way I did that, right, is like for the subset subproblem, I have this target number. For the partition problem, I don't. So I need to kind of get rid of this target value. But I do that by like adding these two fake numbers. And they kind of like force the subset to exactly add to t, because the partition part should add to w plus 1. So then if I add like a fake number that looks like this, I force everything else to add to t, which is the subset I'm trying to find, okay? Yeah, so if that calculation doesn't make sense, like go home and like check that the calculations work out. But just like at a high level, does it make sense? Like, is there a step that you're confused in modulo the calculations, correct? Yeah. But right, like what do we do, right? Like we have to transform one problem to the other, right? And we kind of like understand the structure of the problem to do this transformation, okay? Like we're using the fact that partition has to make things exactly half, and by adding this fake number w minus t plus 1, right, and making sure that the total sum is 2w plus 2, the half has to add to w plus 1, and that forces the rest to add to this target value t. Okay. Okay. All right. So that's all this is saying. Okay. Right. So what we proved is essentially, right, the original input I care about to the subset sum is a yes if and only if the transform thing is a yes for a partition. Okay. Question. So I think there is a problem in the homework where you have to deal with the partition problem. So that's a good reduction. Yeah. So yeah, that's a great question. So the claim is that these two things will never end up in the same partition. That would be bad. And why is that? If I put them together in the same group, like in the partition group, their sum together is already more than w plus 1, right, which is the half. Okay. So I think I have it. Here, right? The two new elements I added, they must end up in different sets. Because if they were together, that sum is already way more than w plus 1. So, right? So that's also a clever thing. Like, I'm forcing them to be in two different sets. Okay. Yeah. So they were, you know for sure that if it's a yes to, right? Like, if it's a yes to the partition problem, they would never end up together. Okay. Yeah. Any other questions? Okay. All right. But yeah, I think, right, previously I said well, okay. Let's keep going. Okay. Yeah. Any questions before we see another example, another reduction? Okay. All right. So the moral is, right, like you have these two like numerical problems, right, subset sum and partition, and they both end up being NP complete. Okay. That's pretty interesting. Okay, so now let's talk about a new problem, okay? It's called bin packing. So bin packing problem is as follows. Okay, I have a bunch of items, okay, and okay, I have a bunch of items of different sizes, and I have some number of bags. Okay, I have k bags, and each bag has capacity 1, let's say, right? We're just it's some unit, 1 unit, and all the items have like size between 0 and 1. And the question is there some way to pack the items in the bags so that they all fit? Okay, all right. So right, you can just think, right? I mean, here instead of capacity 1, it's 8, whatever, right? Then I'm just scaling, doesn't matter. So I have 4 bags, and I have a bunch of items, and they each have like different sizes, and the question is there some way to fit all of this in here? Okay. Okay, so that's the bin packing problem. Right, the fact, like I said, the fact that they're between 0 and 1 doesn't really matter. I can scale it to be anything, right? Or I can scale back. That's just normalization. But does the bin packing problem make sense? Right? Can I pack the items into these k number of bags? Okay. And you can kind of imagine, right? This is a pretty useful problem. If you could solve it, then it would be pretty nice. Actually, for the bin packing problem, it does turn out that there are good approximate ways to do this, good approximate algorithms. We'll see that in a few weeks, or the next few classes. But for now, right, I care about the exact versions. Is it possible to pack it or no? Okay, yes or no? All right. Okay. Does the problem make sense? Please ask. Okay. And right, the goal is to show, okay, bin packing is also NP complete, right? Now I just told you there's 2 NP complete problems. We just talked about partition and subset sum. So we're going to use one of them to show that bin packing is also NP complete, right? So we're going to use the partition problem, right? The partition problem is I give you a list of numbers. Can I divide in half? Okay. And intuitively, right, like, why does this feel like a bin packing problem? Like, anybody have any intuition? Like, partition is asking, can I divide things in half? Bin packing is asking, can I fit all the items in some number of bags? Yeah. Any intuition how these two problems are related? Right. Okay. Right. So the intuition here is that partition is asking really about, right, can I divide in half? So that means I have 2 groups. So it's kind of like bin packing with only 2 bags, okay? So that's why, okay? Right, in the bin packing problem, right, I get to pick the number of items and the number of bins, okay? So that's why it's like a harder problem than partition, okay? So what does that mean? Like, formally, right, I take an input to partition, I have to transform it into a special case of bin packing, right? Another input to the bin packing problem, right? So I get a bunch of numbers, right, in the partition problem. I let m be their sum, okay? Right? The partition problem says, can I divide in half? How can I turn this into a bin packing problem? Well, I just like reimagine the numbers as the size of each item, right? The ith number is the size of the ith item, okay? And I just say, like, can I pack them into 2 bags exactly, where each bag has capacity half m over 2? That's essentially what's going on, right? Does that make sense? Like, if I can do that, right? That's a special case of the bin packing problem, right? I have items with different sizes, but I only say I only have 2 bags. That's a special case. I say, can I pack all the items into 2 bags where the capacity of both of the bags is m over 2, where m is the total sum? Okay. Well, that's I said things are between 0 and 1, but you can scale down by m over 2, okay, so to get between 0 and 1. But the 0 and 1 part like doesn't matter. It's all about packing, right? So that's all this text is saying. Like, to convert to from a partition problem to a bin packing problem, I just say, oh, the number of bags I have is only 2. And I say each bag has capacity m over 2. And I say, can I fit all the items in the 2 bags, right? That's what, And if I can, right, that's a partition. And there's some way, right? Exactly, right? That's what we're trying to say, right? a yes will go to a yes, right? If there is a partition, I just send that to each bags. And if there is a way to packet things into bags, whatever end up in one bag, that's what partition I care about, okay? So yes went to a yes went to a yes, okay? But you know, I'm not even going to show you the text, like, you know, just, does the reduction make sense? I just imagine I have 2 bags. That's the idea. Any questions? Okay. Yeah, so that's the nice thing about having like all these problems, right? It's like, well, they all turn out to be special cases of each other if you reimagine things in a nice way. Yeah, you know, on the positive side, right, what that means is if I have a way to solve any of them or a way to even approximate any of them, that gives me a way to solve all these other problems or even hopefully approximate all these other problems, okay? Right, so it's not like these computational problems exist in isolation. Kind of that's why the theory of P versus NP is interesting. It's saying if I kind of take the viewpoint that polynomial time is the only thing I care about, it gives me a nice way to classify problems, like as like being the same kind of class or in being in different classes, okay? Right. Yeah, any other questions? Like, yeah. Yeah. So the division by M/2 is just a kind of an artifact of how I define the bin packing problem. I said, oh, that items have to be between 0 and 1. Just, you know, that's just a scaling thing. So I can just pretend the items are between 0 and whatever. But yeah, right. If we were actually solving it, like, you know, let's say I have a sum library, right, that can solve the bin packing problem. Like, all I do is I call the library. I don't know how it works. I can just call it. I can just like pip install bin packing. How would I solve a partition, right? I would, let's say the specs or like the input format, right, has to be items and number of bins. And the items must be 0 and 1. What I would do, right, I would scale things down. I would feed this. I would say, as I said, k equals 2. I would feed this into the library that solves bin packing. It will give me an answer, right? And then I have to like undo the division. And I look at which items end up in which bin. And that's the partition I output, right? So in that sense, partition is a special case of bin packing because if I had a way to solve bin packing, I can solve partition. Okay, so yeah, so you know, I gave so that's essentially what a reduction means. I can solve one problem if I know how to solve the other problem. Okay. Yeah. Yep.
Does this mean that bin packing in general is NP complete, or is it just like proving that it's NP complete when there's only 2 bins?
Right, so the general problem can only be harder, right? Like 2 bins is a special case. So because, right, what you can do is you can make the 3rd bin have size 0. Or, you know, like, wait, at least the way I'm defining the bin packing problem, you get to pick the number of bins. So I'm saying if you get to pick the number of bins, then picking 2 bins is just like a special case, right? So the general problem is also, harder, yeah. And that's a great point. Like even like imagine the k-clique problem, right? I give you a graph and a parameter k. So the k-clique problem is like I get to pick the graph and I get to pick the number k. Okay, and I say, does the graph have a clique on 10 nodes? Like that's the, you know, that's the input to the problem is both the graph and the parameter. Here the input is like all these items and this k. Okay, I'm saying if I have a solver that can like solve it for any setting of the parameters, right? That's what it means to have an algorithm for bin packing. No matter what items I give, what number of bins I give, I can solve it. Then I can solve bin packing because I'll just set k equals 2. Okay. Yeah. But you know, like, but yeah, any version of bin packing turns out to be NP complete. Like you can even say like, oh, what if I force that half the items have to be the same size and the other half are uninteresting? You know, some weird artificial version. Like essentially, yeah, any interesting problem turns out to be NP complete. So that's why like the first kind of half of the class where we had all these examples of polynomial time algorithms, that's really actually very interesting that we can even solve these problems because in some sense, like most problems end up being NP complete. Okay. All right. Yeah, so let's just see how the reduction worked. Okay. Right, I give you a partition input. The sum is 24. Essentially what I'm doing is I'm making 2 bins and the capacity of one being half. Okay. And saying, okay, if I can fit all these items where instead of imagining them as numbers, I imagine them as the size of the items. Like instead of this being number 3, I imagine it as an item that has like 3 area or like 3, it occupies 3 units of space. then if I can pack them into 2 bins, then whatever I look at, each of half the size, all the items that end up in 1 bin, well, they have to have half the volume they occupy, which is half the sum. Okay, that's essentially what's happening. All right. Okay, so now we'll see one last problem, and then all of the reductions you'll see is like homework and practice for the final. Okay, which is, first we have the exam and then final much later, but this is the end. Okay, of reduction. So I'll define one more problem, which is pretty cool. So this problem is called the dominating set problem. So first, what is a dominating set? Let me just go to a graph. Okay, so I give you a graph. A dominating set is a set of vertices that dominates all of the vertices. So what does it mean? It means every other vertex is adjacent to one of these vertices. Okay, so it's almost like the vertex cover problem. But the vertex cover problem is about is like covering the edges. Dominating set is about covering vertices. Okay. So for instance, these blue nodes are a dominating set of size 4 because every other vertex is adjacent to one of them. Okay. So that's the dominating set. That's the definition of a dominating set. And now the dominating set problem is like, I give you a graph and a parameter k, and I say, does the graph have a dominating set of at most k nodes? Okay, so here, if I give you this graph and 4, this is yes. If I give you this graph and 3, it turns out it's a no, I think. Okay. Or if I give you this graph and 1, then clearly it's a no, right? Okay. All right, so that's the dominating set problem. And I just wanted to, so this problem turns out to be NP complete. Okay, it's hard to solve exactly, but it looks like artificially like the vertex cover problem. But it turns out the reduction is like really unweirdly like complicated. So if you're interested, there is a set of notes that I put on Canvas where you can read about it. But just like I just wanted to show you this because superficially it looks like the vertex cover problem, but it turns out it's actually a little bit different. It was like very difficult to reduce. Like you could say, okay, maybe I do a reduction from vertex cover, which I know is NP complete, to this dominating set problem. But it turns out to be kind of like hairy to do this. So I just wanted to show you an example of like a problem that seems very similar, but it turns out it's actually a little bit difficult to do the reduction. Okay, but it doesn't matter to this class. But if you're interested, it's in the Canvas page. Okay. Okay, so yeah, so that ends like the actually, yeah, to follow up on the start, right? That's the cool thing about NP completeness in general, is like if I make subtle changes to the problem where it seems like it's almost the same problem, it turns out to be the difficulty turns out to be wildly different. So here's one classic example, which is, right, maybe I already mentioned this, but the 3-SAT problem, right, which is I give you a bunch of Boolean variables. I give you some constraints, right? I say I have a clause of 3 things where I take 3 of them and I OR them, like x1 or not x2 or x5, and x7 or x3 or not x15, blah, 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 right? That is NP complete. That's the first NP complete problem, right? But if I say, okay, 4-SAT, where number of the clauses have size 4, that's also NP complete. 5-SAT is NP complete. 6-SAT, so on. Every k-SAT is NP complete, except if I say, okay, what about 2-SAT, right? Every clause has 2 variables, x1 or x2 or x7. It's like x1 or x2 and x7 or not x15, blah, 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 right? I just have 2 things per clause. That turns out to be solvable in polynomial time. Okay. So 2-SAT, you write the 2-SAT as a graph, and then you do something on this graph, and you can actually solve a 2-SAT problem in polynomial time. So so we went from 2 to 3. It doesn't seem like a big jump, but it goes from polynomial time to being NP complete. Okay, so that's like a cool example of problems where I change the problem a little bit, but the hardness of the problem just like explodes. Another example is linear programming, right? So what is linear programming? I give you a bunch of linear constraints, like x1 plus x2 is at most 5, x7 plus x10 is at most 20, x51 is at least 72, right? A bunch of linear constraints. and I want to optimize a linear function, right? Maximize x7 minus x15, subject to all these constraints. That is solvable in polynomial time. But if I say, OK, I want all the values to be integers. I don't want real values. Right? I say, OK, it's not that x1 is between 2 and 3. It either has to be 2 or 3. Like, I force this integer constraint. Then that turns out to be NP complete. OK, so linear programming is solvable in polynomial time. Integer linear programming, which is I give you a bunch of linear constraints, but I want a solution that's an integer. Like all the values are whole numbers. That turns out to be NP complete. Okay, so small changes in problems make them have very different behavior computationally. Okay. Another example, shortest path. We know how to solve, right? We give polynomial algorithms. Second shortest path, which is I give you a graph, find the second shortest path. That is NP complete. Longest path is NP complete, turns out. Yeah, so all these problems end up, small changes end up being a big deal. Okay. All right, so now let's quickly talk about decision versus search, right? So far, this past couple of classes, right, we've only focused on problems that have yes or no answers, right? I say, OK, I give you a graph and a parameter k. Does the graph have a k-clique? The more interesting version that you might imagine you want to solve is like, well, find the clique, right? That's not a yes or no question, right? It's like return the set of vertices that compromise the clique. Or the bin packing problem, right? I have, you can imagine I'm at a warehouse. I have like some storage units. I need to pack like items in the warehouses. Don't just tell me if it can be done or not. Like if it can be done, find a way to do it, right? Or like, I give you some complicated Boolean formula that represents some constraints. Find a satisfying assignment. Don't just tell me there exists one or not, OK? Or I give you a graph, and I say, does it have a vertex cover, yes or no? Well, find the vertex cover, OK? So that's called a search problem or optimization problem. But so far, right, we've only kind of dealt NP completeness for decision problems. But it turns out it's sort of easy to go back and forth between them, OK? So if I can solve the decision problem, I can solve the search problem, and vice versa, OK? So let's quickly see how it's done. OK? So yeah, so like I said, right, there's all these the decision problems, and there's a natural search variant, right, which is find the answer. Don't just tell me an answer exists or not. Don't just tell me it's a yes or no instance. Show me the solution. OK? OK, so it turns out that for most problems, these two versions are almost the same up to polynomial time. OK? So let's see a quick example. So first, right, if I can find a solution, then of course I can say yes or no, right? If I return the solution, then that's obviously a yes, right? So one way is easy, right, which makes sense. Like if I can find the solution, then answering yes or no is easy, right? If I can find a k-clique, then telling you whether a k-clique exists or not, that's very easy. If I find it, then obviously it's a yes, OK? But now let's go the harder direction, which is let's just say I have a way to solve the k-clique problem, but the decision version. OK, I give you a graph and a parameter. I get yes or no. I want to construct a k-clique if it exists. OK. So let's go the harder direction, right? Which is, right, we're going to show examples where if I have a polynomial time algorithm for the decision variant, where I can say yes or no, then I can actually use it to find a solution. OK. Okay, so let's see an example. Let's just see with the clique problem, and like 99% of things end up being the same idea. Okay, so right, so let's just say I have an algorithm to solve the decision version. Okay, which is there is a oracle in the sky, right? Which I give it a graph and a parameter k, and in polynomial time, right? In time, let's say n to the 5, whatever polynomial time, or n is the number of nodes. It says yes or no if it has a k-clique. Okay, and let's just say it says yes. The graph has a 10 clique. How would I find it? Okay. All right. So what we need to do is, if we assume there is an algorithm for the yes or no question, I'm going to convert it to an algorithm for the search variant. Okay. And the idea is, let me just tell you the idea, and then we can say in words. The idea is well, essentially I'm going to change the graph. I'm going to remove one node at a time, right? And if I happen to remove a node that's in the clique, the answer is going to be no, right? Then I know that node must be in the clique. Okay? So that's the main idea. Let's just say I have a graph on n nodes, and so let's say k is n over 2. Okay? Does there exist a clique that has half of the vertices. Let's say the answer turns out to be yes. This oracle in the sky says, yes, there is a clique. That's super large, a clique. But I actually want to find it. What I do is I change the graph by removing one node at a time. Okay? I take the node and I just remove it, all the edges attached to the node from the graph. And the oracle in the sky keeps saying yes, yes. Then that node must not be important, right? So I throw it away. But at some point, I'm going to remove a node in the clique, and then the oracle in the sky is going to say, no, the clique disappeared. Then I know that node must have been part of the clique, okay? So I found one. And that's how I keep finding one at a time, okay? All right, so let's just say, how do we find the first node in the clique? Well, at some point, if I keep removing vertices, I'll end up removing a vertex that's actually in the clique. I remove that, the graph changes. I ask the oracle, does there still exist a clique? It's going to say no. When I, and then I say, oh, shoot, like that's an important node. That must have been the clique. Right? That tells me at least one vertex in the clique. Okay? And then like I remove that vertex, all its neighbors, and then I recursively find a k-1 clique. Okay? So what's happening is I'm peeling away one node at a time. At some point, I touch something in the clique. The answer the oracle gives is going to turn to a no. I know that vertex must be important. It must be in the clique. So I save it to the side. The graph changes, and I recursively find a k-1 clique. Right? And I'm only making n calls so far to the oracle. Altogether, I'll make maybe n squared calls to the oracle at most. That's polynomial time. Okay? So essentially what I'm saying is if I had a way to solve the decision problem, I can easily turn it into a way to solve the search problem by just asking many, many yes or no questions, okay? So that's why like we focus on the decision problem, because up to polynomial time, they end up being the same. And right, P versus NP is really about separating polynomial versus not polynomial, okay? So let's see another example. Say take the SAT problem, right? I give you a Boolean formula. The SAT problem says, is there a satisfying assignment, right? Is there a way to set the variables to be true or false so that all the clauses end up being true? Right? Let's just say if I only have an oracle that says satisfying or not satisfying, and let's say it says satisfying, how would I actually know how to set the variables, right? How do I know to set this to true, this to false, this to true, this to false? Okay, so basically what I do is I test, right? First I set x1 to false. I simplify the formula, and I ask the oracle, is the formula still satisfying? If it says no, then I made a mistake, right? I should have said x1 to false. Another way to say that, right, it's like, let's just say, right, I set x1 to true, and then I remove x1 from the formula. It simplifies. I ask the oracle, is it still satisfying? It says yes. Then I can freeze x1 to be true. Then I move on to x2. I check true and false. One of these will say, the oracle will say yes, it's still satisfying. That's the value that I can freeze. Okay, so that way, right, I can freeze the value of x1, then freeze the value of x2, then freeze the value of x3, blah, blah, blah. At some point, I'll freeze the value of all the variables, and I'll always have a satisfying assignment. Okay. So it's just solving for one variable at a time. Okay. Okay. Subset sum, right? It's the same idea as in clique, right? Let's just say I have a subset sum instance. I have a list of numbers, target value, and let's say it's a yes instance. How do I find a subset? I remove one of the numbers, and I ask the oracle, is the subset sum still valid? Is there still? If it says no, then I know the thing that I removed must have been part of that subset that I needed. So then I freeze it, and then I move on. Okay. So that's the main idea. Like always, you can turn. If you want to solve the search problem, you can just turn it into a series of like decision problems where you like cleverly remove things, add things, so that yes and no answer kind of helps you reconstruct the solution. Okay, so the whole point of this is like, yeah, why do we only focus on the decision problems? Well, it's kind of without loss of generality. Like it doesn't hurt to only look at the simpler case, because the more general case of search problems are just like you can always solve a search problem by a sequence of decision problems. Okay. Okay. So that's So let me just go to the clique case. Okay. Does the general idea make sense? Like how to turn a search problem to a decision problem? Like. Okay. All right. But yeah, the point of this is just showing that. These special problems that we're looking at, right, where I force the answer to be yes or no, just for simplicity, is really without loss of generality, because the more complicated questions I can ask about clique or subset sum, blah, 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 they're essentially like very many yes or no questions, right? Like imagine doing binary search, right? Like, does this, does this number exist in the array? Or like, give me the index where this number exists in the array. Well, I just ask a bunch of binary search. Is it on the left side, right side, left side, right side? And I can reconstruct the index, okay? So that's kind of the idea. All right. So the last thing is kind of something beyond the class, but it's kind of a cool, cool look into things that we won't have time to cover, some advanced material. All right, so far in class, I kind of hinted at this last time. Right, we have this class P, which is problems that we can solve in polynomial time. We have this class NP, problems whose solutions we can verify in polynomial time. We have this class NP complete, which are all the problems in NP, such that if I solve any of them, I can solve all of them. And now you might wonder, like, okay, so right, clearly P is inside NP, right? We showed that. And NP complete is inside the NP, right, by the definition. But you might be wondering, like, is there sort of a separation between them? Like, is there a problem that's in P, but that's not NP complete? So it turns out that you can show that there must be such problems under an assumption, okay? So if you assume that P is not equal to NP, okay, which we don't know, right? That's a big open problem. But if you assume that's the case, then it turns out there is a way to show some problem exists. Actually, there's no way to like describe what problem this is. It just turns out the proof only says there will be some problem that's in NP, right? But it's not in P, and it's also not NP complete. Okay. So if I assume that like P is not equal to NP, then there will be some problem that's not NP complete and not NP. But of course, like we don't know this. Okay, this is a conjecture, so this is just an assumption. So right, so it's like this theorem says if I assume that's the case, then there is some problem that's not in polynomial time, but it also doesn't turn out to be NP complete. So if I solve it, it doesn't help me solve other problems in NP, and it's also not easy to solve. Okay. Why is this theorem interesting? Is because if I say, okay, what about the state of the world now? Like assuming whatever we know to be true now, can you give me an example of a problem that's in NP but not NP complete and not in P? Every example that I've shown, like, turns out, right, it's either in P, I give you a polynomial time algorithm, or it ends up being NP complete. Like it's as hard as any other problem in NP. There's actually like no known concrete example of a problem where it's not polynomial, we don't know how to solve in polynomial time, or where like, okay, I guess, right, sorry, what do I want to say? Essentially, this is an interesting thing that happens if P is not equal to NP. Okay, so that's all I want to say. These are called like these NP intermediate problems. Kind of like they're not as hard as all the problems in NP. They're also harder than P problems, and they're somewhere in between. Every example that I've shown you so far turns out to be right. Every example of NP problems that I presented, in 3 lectures ago or 2 lectures ago, they were actually all in polynomial time, or they were NP complete. So that's kind of interesting. Like, is there something in between? And there is like a target problem that people think, right, could be an example of such a problem if P does not equal to NP, which we believe to be true. We don't know if it is, but that's kind of the state of the world that we think we're in. Then, right, like this is a candidate problem that could be kind of not in P, so we don't know how to solve in polynomial time, but also not NP complete. Like if I solve this problem, it doesn't help me solve 3-SAT or vertex cover or independent set and so on. So one example, yeah. So this is one example. Like input is I give you 2 numbers in binary, and the question is, does this one number have a factor between 2 and k? Okay. So yes or no question, right? It has a factor or not. This is clearly in NP, right? If I give you a factor, I can just divide and check, right? The division algorithm, it runs in polynomial time. It turns out, but it's not known to be in P. We don't have a polynomial time weight algorithm to factored numbers. And like we also don't think it should be NP complete. Like it doesn't seem that hard. It's a hard problem, but it doesn't seem like as hard as 3-SAT. Another problem that's kind of could be an intermediate problem is called isomorphism testing. So what that means is I give you 2 graphs. Okay, I want to check, are they the same graph or not? Okay, So I give you two graphs, and the nodes are labeled, okay, 1 through n. But the labels in the second graph could be permuted, okay? So I could have shuffled around the labels. And I just give you the graph, and I say, is there a way to map, to reshuffle the labels so that the 1 here corresponds to a 1 vertex, 2 goes to a 2? So like, can I permute the node labels in the second graph and check that the graphs are actually the same? So it seems like an easy problem, but actually there's no polynomial time algorithm to check if two graphs are permuted versions of each other. Right? So what do I mean by that, right? Is like, another way to think about it is I give you the adjacency matrix of two graphs. One adjacency matrix, but the second adjacency matrix, I could have like reshuffled the columns, and I could have reshuffled the rows. Okay, so that means I relabeled the node labels from 1 through n, some other in a hidden way. And the question is, do these graphs, are they same graph or not? Seems like a very simple question, but we don't have a polynomial time way to check. And we actually also don't think that like it should be a hard problem. Like it's not, it's definitely, it doesn't feel like it's hard as 3-SAT, so that's another candidate problem that's sort of in between. Okay, so that's it. Yeah, so that's almost all of NP completeness that we'll talk about. Yeah, see you next time. Okay.